Right, it's 15:45 and I think we should get started. Good afternoon, everybody. My name is Ewine van Dishoeck. I'm a professor here at Leiden University. And I'm happy to introduce and moderate this session on JWST with you. So, what a historic day it was on Tuesday. Of course, starting on Monday evening with President Biden showing the first image from this fantastic new space telescope, JWST. A telescope that has been more than 30 years in the making. And I've been part of the JWST story myself for more than 25 years. And several other of my colleagues that will be speaking here have also been part of this JWST journey for the last 25 years. So it is indeed, it was a historic day and also a very emotional moment for many of us. If you think of the tens of thousands of people that worked in there actually to make JWST happen, to then see the first images and to see them so beautifully and so crisp and with so much detail, that was really a milestone. Fantastic. Good. So here is actually that image that you see here. And this is already the deepest image of the universe that we have today. Maybe we can dim the lights up a little bit so that we can get some of the images even a little bit more beautiful. And my colleague Bernard Brandl will tell more about this particular image in the next talk. Now, for those of you who are not so familiar with JWST, and I can imagine that are several of you, let me tell you a little bit about its history. So, it was actually, as I said, conceived in the 1980s and 1990s, and then it was built and it was finally launched on Christmas Day last year, and it was truly a Christmas present because it was such an accurate and beautiful launch. And this is actually where we saw the Webb actually go. There it goes, yes, from the final stage of the Ariane rocket. And the last we saw actually of Webb, and we could wave goodbye. And we saw it moving away, and then a little bit early then, according to script, there you see actually the solar panel coming out. Yes, fantastic. Good. And then came a very intense period. That was actually a very intense period because it was, many things had to happen. It was folded like this, like a little origami packet in the nose of an Ariane 5 rocket. That's only 4 meters wide. This telescope is 6.5 meters. The sun shield that you see here unfolding is the size of a tennis court. So all that had to happen in the first 2 weeks, and there were more than 300 points on which this could go wrong, but none of that, fortunately went wrong. And so we have actually a telescope that unfolded, as you see over here. There goes the secondary, and now we also have the main mirror there, the panels actually coming out. Good. So, if you want to see more of this also in practice, then please go either to the Boerhaven Museum. There you see a 1 in 10 model in the so-called Grote Vragenzaal. Or, even better, go to the Pieterskerk. We have this 1 in 10 model standing there, and it does exactly what happened in the first 2 weeks in space with Webb. So, it has already been very popular at the reception, and make sure that you also see it. Now, where is Webb actually? Well, Webb is some 1.5 million kilometers from Earth in the so-called second Lagrange point. That is about 4 times the distance from the Earth to the Moon. And there it actually travels with the Earth around the Sun. And in this way, it's a very stable point, and it's such that the solar panel, actually, the solar sun shield, is always oriented such that one side is facing towards the sun and the other one is facing towards space. And why is that needed? Well, Webb needs to be cool, and it looks actually at infrared radiation. We come to that in a moment. And, heat is basically generated by the sun, the earth, and the moon, so it needs to be shielded from those heat sources. So you see here already the temperatures. This was a fantastic website, still a fantastic website to go to. It's very hot on this side, it's very cold on that side. And we were particularly happy to see somewhere in the middle of April that one of the 4 instruments that we are very much engaged with here in the Netherlands and in Europe was actually cold. So, what makes Webb unique? Well, it's big. If you compare it with the Hubble Space Telescope that many of you may have seen the gorgeous images from over the last 30 years, it's about 6.5 meters compared with 2 meters. And that is important for sensitivity. But also, Webb looks with different eyes. So you see here that Hubble actually looks in the light that we see with our own eyes. It's a tiny little part here of the full electromagnetic spectrum from X-rays to radio. Webb actually looks at somewhat longer wavelength in the infrared. So heat actually is what it is detecting. And because there is so much in the atmosphere, like water and CO2, that actually blocks a large part of the spectrum, that's why we need to go to space. That's why we need to have a space telescope. Another reason for going to the infrared is that we have these dusty clouds here. We're very interested in them, but they are actually obscuring the light. You cannot penetrate through them in the optical, but in the infrared, we can actually penetrate into them very well. And a second reason for going yet to the infrared is that Webb was basically designed to look at the very first galaxies in the universe, the very earliest galaxies that you see over here. And these galaxies actually, as they emit, because the universe is expanding, will actually be shifted more and more from the blue to the red. So Hubble was basically stuck. It could not go farther to the red. It could not see these very youngest galaxies that are basically, by the time the radiation reaches the telescope, that they are so much to the red. So that is also very reason for it. Now, we have the Webb, we have the telescope, we have this golden eye, but that just captures the radiation. If we want to do science with it, we need to have instruments, we need to have cameras, we need to have spectrometers with which we disentangle the light into the colors of the rainbow, and that is where we actually do a lot of our science with these so-called spectrometers. And then you can have all kinds of other fancy instruments here on board. There are 4 instruments that do sort of combinations of these cameras, basically taking images and this unraveling of the light, the spectrometers. We are actually, as Europe, involved in 2 of these 4 instruments. One of them is the mid-infrared wavelengths instrument that is sort of the longest wavelengths. That's a European consortium, including the Netherlands, that has built that part in partnership with the US. And then there's the near-spec instrument that was basically led by ESA, largely led from ESTEC, just around the corner here from Leiden. And that is the 2 instruments that we as European astronomers are using a lot, but also worldwide astronomers. These are the 2 most popular instruments on the telescopes. And this shows just a part of the hardware that was actually built here, and that shows you sort of the delicate hardware that goes into these missions. We now know that Webb actually sees sharp. That took a while to sort of get the telescope in focus. And if you compare it with the best previous mission at this wavelength range, you immediately see the sharpness, the incredible sharpness of the images that we have here. Now, what you will hear in the next hour is basically science with Webb, going from first light to new planets. So there have been always 4 science themes of Webb. One of them is the very early universe, the very first galaxies in the universe. The other one is galaxy evolution. Once you form these galaxies, how do they actually evolve? how to become a galaxy like our own Milky Way. You know, we live in a galaxy. Our sun is just one star of several billions, hundreds of billions of stars in our Milky Way. How did a galaxy like the Milky Way actually evolve? Then we have got the life cycle of stars, stellar life, birth, stellar death, and then other worlds, planets around other stars than those than our sun, so other planets than we have in our own solar system. If you want to summarize it, you could also say that Webb actually looks at everything that is old, cold, and dusty. That is sort of a, you can say it like that. So, 5 images were released on Tuesday. The deepest field ever, colliding galaxies, that's what Professor Brandl will talk about. A star-forming cloud, that is what Marina Rashid will talk about. Then a planetary nebula, that's stellar death. And then an exoplanet spectrum, WASP 96b, and that is what Professor Rens Waters will talk about. So today is a big day because the JPEG images were released on Tuesday, but today, actually maybe in a few hours, we are getting all of the data that are now have been taken so far and will be available for us to start analyzing scientifically. So we're all waiting behind our laptops to see this release. Good. Just to give you still a taste. This is such a beautiful spectrum, image, sorry. Planetary nebula, stellar death. This is, you know, what our sun may look like in, what is it? Some 5 billion years from now. Our sun will also run out of nuclear fuel and it will then swell up and start pushing out its surroundings. And this is just an absolutely gorgeous image that shows that process of stellar death. Here you see it actually in the near-infrared camera. In fact, most of the images that have been released are always this near-infrared camera that has the largest field of view and makes the beautiful large images. Here is actually from the mid-infrared instrument. I should also say the colors are such that we go from short to long wavelengths. So, of course, infrared radiation we cannot see with our own eyes. So the instruments actually take images in several filters, just like you can take filters with your own camera. And then the astronomers basically assign a color to each filter so that we can see it with our own eyes. And here the choice of the colors is such that blue is always shortest wavelength and red is the longest wavelength. And so here you see the same in now the longer wavelengths. And now, actually, this is very important. This was always hypothesized to be a double star, a binary star. But that second star, which is a white dwarf, was never seen. And now there it is. You see it beautifully as a binary. So that's just one little gem that we can see already in these data. Another one is the Carina Nebula that you see here in an image taken with the Hubble Space Telescope, which is actually, what you see here is these clouds between the stars. These consist of hydrogen, of gas, and tiny little dust particles. Think of grains of sand that you have on the beach, but then a factor of 1,000 smaller. And these grains of sand actually absorb and scatter the radiation, and that's what makes them look dark. And now here is just a tiny little piece of this Carina Nebula, but now with Webb. And again, an absolutely fantastic image where you see both the young hot stars that have evacuated the cloud, and here then the cloud in which you see all these little tiny dots, which are mostly young stars that are being born at this very moment. They're only some 10,000 to 100,000 years old. So this is, again, one of these beautiful images. Ultimately, we want to link that also to how we were formed. You know, we in our solar system, how our solar system was formed, how we were formed some 4.5 billion years ago. Ben Veriga told already a little bit about origins of life. We can also talk about the origins of our solar system and put that in the context of our nearest neighbor. And we can link that to what we have learned, for example, from other fantastic missions that ESO has done, like the Rosetta mission, actually landing on a comet. But ultimately, that will tell us actually, what makes a planet habitable and how unique we are in the end. So I'll stop here as an introduction and just hope to give you a taste here of seeing our universe in a new light. Thank you very much. We have time for a couple of quick questions, if there are any here. Otherwise, we'll go actually immediately. Oh, here. Can you post your questions here? Yes, no, you can post your questions on Slido if you have anybody who's listening online. But please, also in the audience, feel free to ask. If not, let's actually move on right away to Professor Bernard Bandel, who is a professor here also at Leiden Observatory. He was the deputy co-PI for the MIRI instrument. He is an instrument builder. He is a scientist who works on galaxies. He's also associated with the University of Delft. And Bernard, we're very happy that you're here to tell us a little bit about the instrumentation, but primarily about the extragalactic science that Webb is doing.
Thank you, Ewine. I think I need a microphone. Do I work online?
Oops. One on the table? No, two on the table. Or handheld, you can use this one. You can use that one.
Okay, does it work? Yeah, it does. Thank you. Okay, thank you very much, Ewine, for the introduction. And I will continue not talking about the James Webb Space Telescope anymore. I think you've all seen these spectacular pictures, both from the launch, which was technologically so amazing, but also some of the images. What I would like to do, however, is to advance the slide. And where do I do that? Ah, okay. So James Webb had several hundred potential points of failure, and they all worked. I had apparently only one point of failure, and it failed, but that's why I'm much cheaper giving this talk here than the mission. Okay, so I think that did not solve the problem, Ewine. Okay, good. So now I would like to start with a brief introduction before I show you those spectacular extragalactic images on the science instrument. A few basics, also what Ewine already hinted at, but I think it's really important to understand what we see and why it looks different than what we saw with the Hubble Space Telescope before. Well, one obvious difference is, I think there are two most significant differences. One of them is that it obviously has a much larger mirror. But what does this mean? It has a large mirror. Well, it means if you have a bigger mirror, you collect more light. Yeah, obviously, in the end, the more light collection you have, the fainter objects you can see. So you have more sensitivity, and in principle, you can if the objects get fainter and fainter as they are further and further away, you can look deeper. And there is another reason, and that has to do with optics, namely that you get higher angular resolution if you have a bigger mirror, or a better image sharpness, which is shown here. In these images. This is just a comparison of a previous 40 centimeter telescope, 85 centimeter, and the James Webb telescope. And obviously you see how the image improves. And not only that, when it gets, of course, smaller, you can also see much more detail in between. Now, the other thing is, and now coming to the science instruments, they work at longer wavelengths, infrared wavelengths. And that gives you at least two advantages. One is that infrared light is less obscured by dust. And you have seen the great images that Professor van Dishoeck already showed. But of course, we know that from daily life, if you don't clean the window of your house or apartment, at some point you can't look through them anymore. But when the sun shines, it will still heat up in the summer. Right, so the infrared radiation still penetrates through, and this is, of course, what we also make use of in infrared astronomy. So we see through dust clouds or embedded objects, but you also see objects that are redshifted. And redshifted is due to the expansion of the universe. So if you look at a galaxy in the early part of the universe, where the emitted light at the time was at short wavelengths, say even visible light, if there were aliens able to look at it at the time. But by the time it comes to us, the wavelengths get stretched as the universe expands. And then, of course, if the wavelengths get stretched, it means it's not visible light anymore. It becomes infrared light or even further. And if you want to see then the visible light at the galaxies when they were born, we need to look in the infrared to detect them. Now, there's a problem, however, going from say, Hubble to James Webb. And that's the only equation I put in the presentation here, because I know you all love equations, but it's actually quite simple. The angular resolution, or the sharpness of the image, is proportional to the wavelengths of observing wavelengths divided by the diameter of the telescope. Now, what does this mean? If we want to make this as small as possible, the angular resolution, to see as much detail, to get the best sharp images. And the telescope diameter, well, we went from Hubble to a 6.5 meter James Webb mirror. But we also went to infrared light, and that increases the wavelengths. So essentially, those two effects, that gets bigger, and that gets bigger, they almost cancel out. So the net result is almost zero in terms of resolution. So just based on that simple thing, I would expect that James Webb will be much more sensitive than HST because it has a much larger telescope mirror. It will see many more dusty objects, for a reason we said before, but it will not necessarily provide sharper images than HST. So don't expect something that is now super sharp compared to what we saw before. Now, with that introduction, briefly on the instruments. There are 4 science instruments on James Webb, and Professor van Dishoeck already talked about MIRI. MIRI was built, and both Ewine van Dishoeck and I were involved in that project, so we really love this one. Of course, all instruments are great and work equally well. But this is the mid-infrared instrument that really goes the furthest in wavelengths, and maybe you can argue also therefore provides the largest discovery space, but that's debatable. There is the NIRCam, the imaging camera that was built in the US. NIRSpec is an instrument from ESOF that was built very close to here at the ESTEC facility in Noordwijk. And then there is the Canadian instruments, the fine guidance sensor would primarily make sure that the James Webb Telescope is pointing at the right location, but you can also use it for science, and there is a spectrograph involved as well. If you want to look how these things actually look in how these look in reality, this is it's big, and it contains a lot of money and the work of thousands of people, what you see here. But these are the 4 instruments before they were integrated in the spacecraft. Now, okay, enough introduction. Let's talk about the first extragalactic image. And before I show you the James Webb image, let me just say that this is, of course, a famous group of galaxies that was discovered by Edouard Stephan about 145 years ago. And, well, it's called Stephan's, well, that's obvious, quintet, because there are 1, 2, 3, 4, 5 galaxies in here. This is an amateur image, and I picked this deliberately just to show you the improvement between what you can do with a very good amateur system from the ground and what you will see then. And there are those 5 galaxies. Now, it turned out later that actually this one doesn't belong to that group of galaxies. It just happens to lie in the same line of sight. So those belong together, and they're actually swirling around each other, and at least those 2 are closely interacting. They will not merge, but they're interacting, and so there's a lot of interesting stuff going on in that region. Now, this is also for comparison a Herschel image of that same region, which already gives you a lot of information. Look at the colors. This one looks very different from the other ones, but the problem, of course, the Herschel is a 3.5 meter telescope working at very long wavelengths. What we said about the resolution before, it's very difficult to go in there and study structures in these galaxies because the resolution is so bad. And I'll skip the right one here. And we'll straight go to the HST image as a reference point. So this is what the Hubble image looked like, taken with their wide field camera 3 a couple of years ago. And this is what the James Webb NIRCam and MIRI image look like. As Ewine said, this is a combination of different filters to create the colors, right? Because it's obviously not visible, but you can take the filters from NIRCam and MIRI and combine them in the same way as your smartphone would compose a natural color image by looking at different pixel filters that are in your cell phone. Now, okay, of course, it's already clear it looks very different, but let's make a couple of comparisons here and look what we see here. Well, first of all, whenever you see something with these spider structure or hexagonal diffraction spikes, then it's foreground stars. So these are point sources in the foreground. We don't study them usually, so they're more or less of a nuisance in the image. But what you also see in addition to these 5 galaxies here, again, remember these are 2 actually that are in the process of, well, they're interacting. And so every time they pass each other, they pull out some material from the other just by gravitational attraction. And so you see these arms here. Actually, that arm here, there is an arm sticking hundreds, millions of light years into space here. And let's see, what else do we have? Yeah, let's just look at this galaxy here and making a zoom in a high color image. So I hope you can see all that. Isn't that fantastic? So there are thousands of stars you can see, and this is a galaxy like, I mean, we're used to images like that from our Milky Way, but now you see all these stars in the different colors, of course, at the galaxy, which is 40 million light years away. Now, okay, this was what we looked at, the near-infrared and mid-infrared image composed. What would the mid-infrared only tell us? Because, as we said, our love is with the MIRI instrument. So what if we had only MIRI instrument? What you would get then is essentially not the stars anymore. You would be much more sensitive to, so this is a subset essentially of that image. And what we see is that the stars don't show up anymore because the stars themselves, they are not very bright in the mid-infrared. But what you see here is the interstellar medium, the gas and dust that fills the space between the stars. And it's also interesting because this one, what appears to be very bright here, this is an active galactic nucleus. And a supermassive black hole in the center of the galaxy that's actively accreting material. Now, how can we find out more about that? Well, we can use the MIRI instrument and take a spectrum. And this was done here in 2 locations of the galaxy. So this is our quintuplet or quintet. And then there is here somewhere a spectrum taken. And I can't go into the details here, but the main point simply is there is an incredibly high signal to noise or clarity in the spectra that you can use to analyze their chemical content, as shown here with all these species, these chemical species that are in there. And of course, not only the existence of those, but also how strong those lines are, give you an idea what the temperature is of the gas, what the pressure is of the gas, and so on. And then there was another spectrum taken right at the center of the galaxy, and that is shown here. And again, I don't have the time to dive into that, but this will, of course, be the subject of many studies. Now, I said accreting black hole. What does this mean? So there is material, gas in the center of the galaxy, and it's swirling in. Eventually, it will be swallowed by the supermassive black hole. But before it gets there, it does not fall in straight away. It does what if you take the plug out your bathtub, then the water will not just straight flow in, right? And when it gets lower, you see the water starting to swirl around the outlet in your bathtub, and essentially the same happens here. So it swirls around, but it does that at incredible speeds, and it heats up. And because it heats up, it will shine very, very intensely. Now, we can study that, again, with the MIRI spectrograph. So we took integral field spectrum, we don't have to worry about here, but it's essentially a spectrograph which gives you spectral information for numerous positions in the field. And then you can analyze them for the different species, for the elements that we saw in the spectrum before, and then look, because of the Doppler shift. Yeah, if you say the observer is here and looks at this disk here, so if it's, say, it's turning counterclockwise, I don't know how, but let's say, then this part would come toward you and will be blue shifted, while this part recedes from you and will be red shifted. And this is already, we can see that. So part of that central part is bluer, part is redder. And so we can distinguish between these different components and find out what the velocity of the gas is. And I see Ewine is getting desperate. So let's go to the deep field. And what does deep field mean? Well, you pick a point on the sky that looks boring, and you'll integrate for a long time with your instrument. So you look further and further, as longer integration times, you have more sensitivity. And of course, this is a NASA slide. So the point here is we really want to see not the galaxies that we already know, but the galaxies in their infancy, when they were born, how they evolved, how they grew. And this is, of course, most interesting at the very earliest stages. And this was one of the main reasons why the James Webb Space Telescope was built. And so the deep field, how large is it? Well, if I tell you 2.4 arc seconds, it may not tell you much, but look at the full moon. Well, everyone has seen the full moon, and you just pick a small square like that. This is the field size of the James Webb Deep Field. And this is what you find in there. Yeah, so actually it was focused on a galaxy cluster here in the center, but the amazing part here is not the galaxy cluster that it was pointed on, but all the galaxies in the background that you can see. And well, this is just an enlargement of the same image. And since I'm sure people in the back at least will still not see every galaxy, and well, let's not discuss the details here. What is important, though, to point out is that some of these galaxies appear to be very elongated. And this is just due to gravitational lensing in the sense. So the mass of the cluster really bends the light. And so what you see here is the light from a background galaxy that is affected by the massive concentration here in the center. But let's move on and just pick out this part here and zoom in on that one. I randomly picked that one. I could have taken any other one, but just to see you, because there are many more small, and all of these objects you see here essentially are galaxies. They're not stars. And so there is a wealth of features, different colors, different shapes that, of course, have to be analyzed. And now, wouldn't it be nice to see what Hubble Space Telescope had in comparison before? So I looked up the Hubble images, and this is essentially what Hubble found in their ultra deep field or their equivalent deep field. And this Hubble image that took weeks to take, so those were really weeks of integration time, and this image was taken in 12.5 hours with the James Webb Space Telescope. So this is really the improvement that you get and that you can play. And of course, again, if you look at this image that was also observed with MIRI at longer infrared wavelengths, you see a very different view of the universe. In particular, what you see here are some suspicious green objects which show a very strong hydrocarbon emission. So they're very actively star forming, in addition to other distant red galaxies. And of course, there is still the foreground galaxy in the center. So there's plenty of more thing to do, and I think it's very fascinating, but this was just the beginning. Thank you. Yeah, yeah.
Can we detect in this field?
How many?
How many stars, how many galaxies detect already?
Oh, I don't know about the galaxies because I had one day to prepare that talk.
I think there are close to 10,000.
But stars, it's just a dozen in that same field.
Stars, just a few. Yeah, I think that. Yeah, go ahead. Ask a question.
I mean,
Yeah.
I'm not sure what we do with the.
Yeah. We first give precedence to the people in the audience. Yeah.
Possible to get spectrographic information from the galaxies that are lensed?
Absolutely.
It is.
Absolutely. It would have, you could even, simple test would be you could check your model and look at some lensed image on the right side and some lensed image on the left side, and they should be the same, right, the spectra. But it hasn't been done as these early release observations.
Would it be possible to get the Slido questions on the screen? And then, go ahead.
Maybe you already mentioned it. I was a little bit late. But what's going to happen next with all these with all this footage? So who's going to be crazy about all the things we see, and what can you see in the picture that's worth investigating further? I'm curious what's going to happen next with these pictures.
You want to take that one?
Well, first of all, there are probably as many astronomers interested in the data as there are galaxies on the image. So I'm not worried. We have to give some patience, of course. These are spectacular images. There will be others as well, similar fields, different groups, some probably going even deeper. There are big consortia looking at that. It's not that NASA just pointed the telescope somewhere and said, here, someone look at it. There were big plans, and that's also reflecting the interest of the community and the groups who have very well-defined plans how to analyze the images. And the beauty of, generally the beauty of astronomy, but also of a multi-purpose instrument like James Webb, is that you take on one observation, and there's so much information for many different interest groups. So depending on whether you look or interested in gravitational lensing, like our esteemed colleague Koen Kauken, who is also sitting here, or
Short.
okay.
Yeah.
Okay, I mentioned Koen, we can go on.
No, because this actually fits in very well with one of the questions that came in. There's an incredible sense of collaboration. This is from Sean Sapcario. There's an incredible sense of collaboration, team pride, open sharing of data, and lack of individual recognition in this achievement. How does this happen, and what advice? Oh, there we go. And what advice would you have for other fields to achieve these same goals? And I think this is indeed the spirit that we have in these big collaborations. Is that it's a team effort, and that is really, we are celebrating the success of everybody, from the scientists to the technicians to the managers to the system engineers. Everybody has played its role in making this happen. There was another question that was on the time resolution of these images. Would you get the same one if you took it a few seconds later? The answer is yes. In most cases, there are some phenomena definitely that's going to change on timescales of years. That's Webb can follow, and maybe a few things that are really time sensitive. But the bulk of the images simply don't change on timescales of over the whole lifetime of Webb. Yeah. Good. With that, let's thank Professor Brandl again. And
Thank you.
then we go to Marina Rashid. So Marina is a PhD student at Leiden University, working with Professor Harold Linnaerts in the Leiden Laboratory for Astrophysics. Marina actually did her master's in Brazil, and we are very happy that she came here because she has been doing so much work in preparation for Webb that she is now in her final months of her PhD. She is seeing this coming to fruition. Marina.
Yes? Hi. Okay. Thank you, Professor Ewine, for the introduction. I'm Marina, and I will be talking a little bit another side of the discoveries with James Webb. So for this, I want to start with this beautiful picture of Carina Nebula. And I want to guide you through some points on this picture. And what is this picture? It shows a cloud where massive stars have just born. And what are these clouds? So inside our galaxy and other galaxies, we have gigantic clouds of gas and particular material that we call dust. And these clouds, they are gigantic, and they fall under their own gravity, forming stars. And that's what has just happened here. So above this imaging of somewhere that we cannot see here, there are massive stars. And these massive stars, they are irradiating light, and this light is pushing away the material that has just formed the stars. So you can see here the material of the cloud surface, and there is a cavity here where the stars are. And yeah, Webb has just revealed the surface of this cloud, and you have a lot of structures here, and sprinkled everywhere you have other stars that are born inside these clouds. So here you have a picture of a part of Carina Nebula from where this image was taken. So this is a part of the Carina, and this smaller part is the part that Webb has looked at. And we also have looked at, to this region with Hubble. And as Professor Evina and Bernard said before, Hubble was a telescope that could look at visible light. So we're looking at different things here. With Hubble, we are looking to the exterior part of this cloud, while James Webb can actually look inside the cloud, where like the locations where these stars are just born. So the infrared light, the dust doesn't scatter the infrared light as it scatters the visible light. So basically the cloud is transparent, and we can look inside of it with James Webb. So if you download this image at your home and you zoom in, you're going to see a lot of small points that are the baby stars born in there. So what James Webb is adding to the star-forming region field is the opportunity to study with a very sensitive and powerful instruments the physics and the chemistry in the first stage of stellar evolution. So from now on, I want to talk a little bit about this dust that has blocked the Hubble light from us. So if you look at these clouds, inside of them, you have very cold temperatures, and you have this dust material that's made from carbonaceous and silicate material. They're about 1 micrometer size. And because the temperatures are so low in there, atoms and molecules, they will stick in these grains, and they will form a layer of frozen material that's known as interstellar ices. So you can see it here. And a lot of laboratory work has been shown that many molecules can be formed on these ices. So you have chemical reactions in there. But how can we see the molecules that are present in these ices? For this, we have to look to a young star. So a young star emits light on the infrared, and this infrared light will pass through the cloud, and part of this light will be absorbed by the material on the solid dust grains. And it's looking at the absorption of part of the light was absorbed that we can identify the molecules in there. Let me show you how. So molecules, when they absorb infrared light, they can vibrate. And here you can see an example of water. So water can, you cannot see in the color, but here, these vibrations, they give rise to this band here. This is the infrared spectrum of water taken in the laboratory. So we freeze water in the laboratory, and you shine infrared light, and you see how it's absorbed this radiation. So this band is generated by these vibrations here, where the oxygen and the hydrogen, they go far apart from each other. So every vibration gives rise to one different band in the spectrum. And this characterizes the spectral signature of every molecule. It's characteristic of every molecule. So if you have this spectra and you compare this with the observation, you can tell which molecules are in there. So this is the lab spectrum. This is the lab spectrum. Let's look at the observation now. So this is a spectra taken from a past infrared telescope from a massive star, and what you see here is the light from the star, but you can see some depths here, and these are absorption bands of molecules that are in the ices. So if you compare this with laboratory data of these molecules, you can name them, you can identify them. So here I have the same region in this area as the water would absorb, and you can see here a band of water, and you can also identify another band of water here, that is this one here, and so on. So doing this comparison, you can identify this molecule. And you can see that a few molecules have been identified in this object. But the situation is a bit more complicated, because if you zoom in a small part of the spectra, you actually start to see some small wigglings. And because of resolution and sensitivity of past infrared facilities, we actually could not assign these small bands. But they are also probably like to organic molecules. And we hope that soon we're going to be having results of James Webb that will tell more about what organic molecules are in there. So a bit more complication to the situation. If you look to a molecular cloud, the different parts of the cloud, they have different temperatures. For example, the outer parts of the cloud, they are a bit warm, and the interior are colder. So as you go to the interior of the cloud, you have a different chemical composition of this ice material. And when you look towards a star with James Webb, we're going to see all these ices that are absorbing between us and the star. All these lines along the line of sight. And because the absorption of the molecules, they are very sensitive to the other molecules that are in the ice and to the temperature, when you look at absorption band in the astronomical observation, we're going to be seeing a composition of all these different components of the molecule in different environments. And this actually requires a lot of laboratory work to compare and to support the observation. And here is just an example. So this is one band, a band of carbon dioxide observed towards many protostars. And the band has different profiles. And what I want to show here is that this color components here is the absorption of carbon dioxide when you mix with different molecules. For example, this red is when you mix with water. If you have pure carbon dioxide, you have something that looks like this yellow band. And the message that I want to give you here is that for understand the profile of this band in many objects and take some physical interpretation, physical information about the environment of these ices, we have to have a collection of laboratory data to fit this band. So said this, I want to introduce you quickly about the work that we have been doing in the Laboratory for Astrophysics here in Leiden. And this is a laboratory that we have many experimental setups that we use to investigate spectroscopy, chemical reaction, and the destruction of molecule in interstellar simulated conditions, both in the solid and the gas phase. You can see here a picture of the laboratory. And if you want more information, you can look at the webpage of Professor Harold Leonard's. So one of the setups that we have in the lab is called Arasis. And on this setup, you can recreate the conditions of the interiors of molecular clouds. That means vacuum and very cold conditions. So we have a vacuum chamber with a crystal in the middle. In this crystal, we can grow a layer of ice with whatever composition we want. And we take the infrared spectra of this ice. And we also characterize some other parameters of these ices. And all this data is publicly available through the Leiden Ice database. So here you have the interface of the database, and you have also some organic molecules that we have been studied. You can choose your favorite molecule. But just to give a flavor here, I will show you how these differences are in one of the molecules we studied. That is acetonitrile. So this is a molecule that has been studied, that has been identified in many other environments in the interstellar medium. And we have created a synthetic spectrum using laboratory data as input to see how the absorption band of this molecule would change. And here I would just give one band just to see the difference. And here we have mixed this molecule with different components and see how the position, how the width, and the intensity of the band change. And this is the band of the molecule. And you may say, it doesn't change that much. So now you have to believe me. It does. It makes a lot of difference because when you look at the real interstellar ice data, there will be a lot of more components here. It may have a lot of more components here. And if you want to characterize and identify and quantify this molecule, you actually have to have this laboratory data to back up your observation. And this especially when you have MIRI spectra, because with MIRI you're going to be seeing what we call the fingerprint region. That is where we can identify many of the organic molecules. So it will be essential that we actually use this laboratory work and the observation, they work together to interpret what we're seeing there. And last but not least, I want to talk to you briefly about ICH. That is an early release science program led by Melissa McClure from Leiden University. And this is a program that has been granted with 33 hours of work of James Webb that will be around 15 hours of observations. And this program, we're going to look to different objects in different stages of star evolution to actually see how the ices are formed and how they evolve chemically along the stellar evolution. And this actually will give us information about how organic molecules are formed in space, and will help also to interpret observations that we see of these molecules in the gas phase. And with this, I want to leave you with with some take-home messages that James Webb will bring a golden era for ice observations, and that will have a big impact as well on the interpretation of the gas phase observations that we have with telescopes on the ground base, and that laboratory data will be essential to understand what we're seeing. Yeah, thank you.
Thank you very much, Marina, and highlighting also the importance of other types of preparatory work, not just building an instrument, but making sure you also have the data to analyze it. Are there any quick questions from the audience? Yeah, go ahead. Yeah. Sorry, I don't know whether. Yeah.
Will you be able to find, what about molecules that don't exist here on Earth? Do you ever see that, and do you think that that will be an outcome of James Webb?
Sorry, molecules that can exist where?
Because you use molecules from Earth to work out what the wave would look like. So what about molecules that don't exist on Earth?
Molecules that we normally don't have on Earth, or that would exist.
Oh.
Yeah.
Right. Yeah. Actually, there are places in the interstellar medium that have a quite exotic chemistry, and these places are usually on the gas phase, and that is because on Earth the densities are much higher. So these molecules that are very unstable and exotic, they would quickly collide with something and react and disappear or become something else. Disappear, no, they will become something else. So if you have them on the gas phase, on this very diluted medium, they can survive for a long time, and you can actually see them. On the ices is different, because the ices, the molecules are very close together, so very exotic molecules, or that we wouldn't see very often here on Earth, they wouldn't survive for long times.
Yeah. Another quick question there, yeah?
Yes. Why are the borders of the clouds so sharp?
Why are the borders of the clouds so sharp? Yes.
Yeah, they are always very sharp in all kinds of wavelengths, and I've always wondered why. There should be an explanation of that. They could be fuzzy, right? I mean, in fact, it would be more normal than to be fuzzy. So why are they so sharp?
So I have an idea, but I'm not sure. That I would say that they pick the wavelength that they are observing at to trace features and things that are changing to give these beautiful images.
Yeah, in this particular case, the UV radiation from the bright stars is actually pushing on the cloud and creating these very sharp boundaries. You actually see it photo-evaporating. You see the material streaming off the cloud. So yes, that is something that will change with time. It's basically eroding the cloud. Yeah. I see this question here. I will take that at the very end, actually. This is a good question, but let's take this at the very end from Hendrik Bergenaar. So keep this message on Slido, but we'll move on now to the final talk, which is going to planets. Not planets in our own solar system, but planets around other stars than the Sun. And Professor Rens Waters from the Radboud University, the former director of the Esron Institute, will actually tell us about some of the first results from Webb in this topic.